Have you ever stopped to think about how we actually measure something as powerful, as absolutely massive as an earthquake? Well, it turns out the secret lies in a special mathematical tool that helps us make sense of nature's most incredible forces. It's how we turn pure chaos into numbers we can actually understand. So let's dive in and unlock this thing.
Okay, let's look at a couple of real-world examples. In 2010, Haiti was hit by a magnitude 7.0 earthquake. Just a year later, Japan was struck by a 9.0. Now, when you look at those numbers, 7.0 and 9.0, they seem pretty close, right? I mean, it's just a difference of 2. But in the world of earthquakes, that tiny little difference means something way, way bigger.
So let's put the question on the table. How much stronger was that 9.0 earthquake in Japan? I mean, was it twice as strong? Maybe like 10 times stronger? Whatever you're guessing, I promise you the real answer is not what you'd intuitively think.
Get this, that 9.0 earthquake wasn't just a little stronger. It was 100 times stronger. Yeah, you heard that right, 100 times. This is where you realize that the Richter scale is not a normal linear scale at all. It's playing a completely different game.
Okay, so to really get our heads around this, let's try a thought experiment. Let's say we know one earthquake was 500 times more powerful than another one. How would we even begin to calculate the difference on the Richter scale?
Well, the math problem would look something like this. 10 to the power of x equals 500. That x is the difference in magnitude we're trying to find. And we can kind of ballpark it, right? We know 10 squared is 100, and 10 to the third power is 1,000. So our answer, x, has got to be somewhere between 2 and 3. But that's the problem, isn't it? How do we find the exact value? None of our usual algebra tricks are going to help us solve for an exponent that's stuck up there. We've hit a wall. We're missing a piece of the puzzle.
And this is where the hero of our story comes in. To solve for that missing exponent, we need a special kind of function that was literally invented for this exact problem. We need the logarithm.
So what on earth is a logarithm? Honestly, at its core, it's super simple. A logarithmic function is just the inverse, the mirror image of an exponential function. Its entire job, its whole purpose in life, is to find the exponent. That's it.
We've all seen this a million times, right? The exponential form. You've got a base b, you raise it to an exponent y, and that gives you some number x. You know, like 2 to the power of 3 equals 8. Simple.
Now the logarithmic form just takes those exact same 3 parts and shuffles them around. It says, hey, if I know the base b and the final number x, I can tell you what the exponent y was. See how the exponent is now the answer, all by itself?
Okay, this is it. If you remember one single thing from this whole explainer, please make it this sentence. The logarithm is the exponent. Say it again. The logarithm is the exponent. That one idea makes this whole concept so much easier.
And here's a great little mental trick to help you remember how to switch back and forth. Just say this little phrase to yourself. Base to the exponent gives us the number. It's like a little loop that always works. Let's see it in action. Take a look at these. 2 to the third is 8. That becomes log base 2 of 8 equals 3. 5 squared is 25. That becomes log base 5 of 25 equals 2. It even works with negative exponents. See the pattern? Every single time, the logarithm just grabs that exponent and puts it on the other side of the equal sign.
Okay, let's try one out right now. What is log base 2 of 8? Don't let the notation freak you out. All this is asking is, 2 to the power of what gives you 8?
And the answer is 3. Because 2 times 2 times 2, that's 2 cubed, is 8. See? That's all there is to it. You're already solving logarithms.
All right, you ready to level up? What about log base 3 of 1 over 27? Again, just ask the question. 3 to the power of what gives me 1 over 27? That fraction is a big clue.
The answer is -3. Remember how negative exponents work? They basically just flip things into a fraction. So since 3 to the power of 3 is 27, it means 3 to the power of -3 must be 1 times over 27.
Now, there are 2 special logarithms you're going to run into all the time. The first is called the common logarithm. It always has a base of 10. It's so common, actually, that if you just see log x written down without a little base number, you just assume the base is 10. And this is the secret language of the Richter scale.
The other special one is the natural logarithm. Its base is this weird, famous number called e, which is about 2.718.
you'll see it written as lnx. And trust me, it is absolutely essential in science, calculus, finance. It shows up everywhere.
Okay, so now that we have our awesome new tool, let's go all the way back to that problem we got stuck on before. What's the difference in magnitude if one earthquake is 500 times stronger than another?
Let's break it down. Step 1, we start with our original equation, 10 to the x equals 500. Step 2, we just convert it to logarithmic form. And since the base is 10, we know we can use the common log. So step 3, x equals log of 500. It's that easy. And now you can just punch that into any calculator, and boom, there's our answer. The difference in magnitude on the Richter scale is about 2.699. So an earthquake that's 500 times more powerful is only about a 2.7 jump on the scale. Wild, right?
And this really shows you the true magic of logarithms. They're like scale shifters. They can take these gigantic, mind-boggling ranges of numbers, like the energy an earthquake releases, and compress them down into a simple manageable scale, like 1 to 10. They make the incomprehensible comprehensible.
And that just leaves us with one final thought. The Richter scale isn't the only place this clever trick is used. From the loudness of sound, which we measure in decibels, to the acidity of liquids measured in pH, our world is packed with these secret logarithmic scales. So it makes you wonder, what other parts of our world are being measured this way right under our noses?